Hi, my name is Anfu and my partner is Pavan Pandarangi, and today we're presenting edPCV, which is Environment-Driven Prompt Completion Variance, which is a novel methodology for risk assessment in LLM-guided robot actions. So basically the problem that we have today is that we want to ensure that robot actions that are instructed by large language models are safe, and this is critical to minimizing potential damage. But human commands are often ambiguous and potentially dangerous. For example, if I said to this robot on the right to microwave the bowl, if it chose the wrong bowl without asking for clarification, it could put in the metal bowl and potentially hurt a lot of people. And what we want to do is minimize the interactions with the user while maximizing the execution speed and effectiveness of these commands to execution. Our goal is to build an LLM-Robot perception and manipulation pipeline that encodes statistically guaranteed uncertainty and asks for help but only when needed and otherwise executes the action. And we want it to take natural language commands and manipulate a generalized set of objects from Cheez-Its to Pringles cans to mustard bottles to fruit, etc. and achieve 90% plus accuracy. So now I'm going to walk you through how we implemented PCV prompting on the LLM side. So you can see the prompt here, in which we use few-shot prompting as well as role-playing to maximize the effectiveness of the prompt. And we feed in the object list that's seen by all the cameras at the bottom, as well as the user command. And it outputs the chosen object guess. Then we have two hyperparameters. One is a conformal prediction threshold, which is set at 90% to allow for a statistically guaranteed percentage threshold. And our second hyperparameter is the amount of calls made to the language model with the prompt I talked about previously. And what we do is we automatically standardize the output. So we remove all quotation marks and punctuation and capital letters in order to automatically quantify the uncertainty and confidence of certain choices from the many responses. And one interesting thing is that we noticed on multiple models that there was heavy bias on the first choice in the list on ambiguous commands. So for example, if you had a list of a mustard bottle, a soup can, and a sphere, it would 4 out of 5 times choose the mustard bottle when the command was ambiguous. So what we did to fix this was we randomized the list order in order to eliminate that bias. Next, I'll walk you through how we implemented the technical pipeline from start to finish. So first, we have multiple camera views that the robot sees in its environment of different objects, as well as the user command. Then we use mask RCNN to list all the scene items in each camera view, and we send this list to the prompt in the query and prompt it multiple times and calculate the dominant choice based on the conformal prediction threshold.
If the LLM is able to find the object that we're interested in picking up, we can use the mask RCNN algorithm to calculate a mask for that object of interest. Using the depth information found in the camera's image, we transform this mask into a point cloud. Then, by aligning the normal vectors of the point cloud points in the gripper, we select optimal antipodal grasp candidates, at which point we can construct a trajectory for the robot to pick up the object of interest. Now, if the LLM isn't able to find an object of interest based on the prompt, it doesn't go forward with this process and the action is instead canceled. We ran trials on 15 different prompts, where 5 were well-defined, correct prompts, 5 were ambiguous prompts, and 5 were erroneous prompts. For each of these classes of prompts, we further generated easy prompts and hard prompts, where hard is defined as requiring background knowledge about the object of interest. We observed a correct classification and execution rate of around 93%, which is an indication that our method serves well at its intended purpose of identifying risky behaviors. In the future, we hope to allow the LLM to also see the camera's image, allowing it to gauge visual cues in addition to the prompt.